Energy and stability. This rock has potential energy due to its mass and height. Once it's pushed over the edge, it falls to the ground. When at rest on the ground, its original potential energy has become heat in the rock and its surroundings. We will use heat and thermal energy interchangeably, though there is a distinction you will learn later. A rock on the edge of a cliff is unstable. It could stay at the edge for a long time, but given a small push, it will continue to fall until it hits the ground. Once on the ground, it is stable. It can't fall any farther. The rock at the bottom of the cliff is stable. No matter how long you wait, the rock will not fall back to the top of the cliff. The heat energy from its fall cannot launch the rock upwards. To get the rock back to the top, it would have to be carried there. That would require the same amount of energy that became heat when it fell. Falling down is spontaneous. No outside energy is needed once it is started. Once begun, the skier continues down the hill. Falling up is non-spontaneous. Energy is needed to get the skier back up the hill. Energy is stored in chemical bonds. Chemical reactions are the rearrangement of atoms, forming or breaking chemical bonds. When atoms fall together to form a bond, energy is released. It then takes energy to break the bond, to separate the atoms. So here you can see a bond is formed and some energy is released, and here we add in some energy and a bond is broken. Reminder: a covalent bond forms when atoms share electrons in order to have a stable number of electrons. A covalent bond that yields a more stable system will form spontaneously. Covalent bonds can be very strong. It can require a large amount of energy to break them. In fact, the energy needed to break the bond is equal to the energy that was released in forming the bond. Just like the energy needed to carry the rock back to the top of the cliff is equal to the energy released when it fell down. Chemical reactions can go in both directions. Products can be reactants, but they tend to be spontaneous in one direction and non-spontaneous in the other. The energy released in the formation of the bond equals the energy that must be added back to separate the hydrogen atoms. Hydrogen atoms are more stable when joined together into an H2 molecule than they are when they're separated. You can think of the hydrogen atoms falling together to form H2. Two separate hydrogen atoms are unstable. Once they get close to one another, they will spontaneously form a molecule of H2, releasing energy. Apart, they are unstable, and it's just a matter of time until they come together, form a molecule, and release energy. Just like it's just a matter of time before the rock falls off the cliff. Stability tends to increase over time. H2 is more stable than H. In spontaneous reactions, the products are more stable than the reactants. Breaking apart H2 requires that the same amount of energy released during its formation be put back into the H2, like carrying a rock back to the top of a cliff. In the case of the rock falling off the cliff, the potential energy ends up as heat. The same thing happens when H2 is formed. Heat is released when the atoms bond together. We write plus heat or plus energy released in the equation above to remind us that heat is released.